Alright, in this video we'll be going through the 2017 Waves exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you completed the question or get stuck, unpause the video to see how I go about getting the answer. A Dutch physicist demonstrates the Doppler effect by listening to musicians playing their instruments on a train as it passes him. One musician played a note on a clarinet with all finger holes closed. A clarinet can be modeled as a pipe that is open on one end and closed at the other. The length of the clarinet is 0.631 meters, and the speed of sound is 341 meters per second. On the diagram below, draw the first harmonic, which is the fundamental frequency standing wave, and label the nodes and antinodes. Alright, so like it says right over here, this is an open and closed-ended pipe, and so for that we know we must have a node on this end and an antinode on this end. And as we're drawing the fundamental frequency, these are all the antinodes and nodes that will be in the wave. And so therefore we can draw our wave as so. And as you can see, our length is equal to 1/4 of a wavelength. There we go. The clarinet produces the fundamental frequency and several harmonics. Explain why the clarinet does not produce any even harmonics. So as this clarinet is modeled as a open and closed-ended pipe, we must have a node on the closed end and an antinode on the open end. Obviously that was our first harmonic. Okay, we can redraw that over here like so. Okay, and if we do our first overtone, which will be our third harmonic, okay, we would have an antinode over here, a node over here, an antinode over here, and a node over here. And it will look something like this, okay? Now let's do the next overtone, okay? Antinode, node, antinode, node, antinode, node. And therefore it would look something like this, okay? So the point I'm getting at is we know that this length is equal to 1/4 of a wavelength, okay? And the reason why we know it's 1/4 of a wavelength is because if you haven't watched part 2 of my standing waves video on my waves playlist, you can go check that out. But if you have watched it, you would know that we can find every half a wavelength via successive nodes or successive antinodes, okay? So if we have successive nodes, that means we'll have an antinode in the middle and it will look something like this. And if we have successive antinodes, that means we have a node in the middle and it will look something like this. And so successive nodes or successive antinodes equals half a wavelength. However, if we have a node met with an antinode, this is half of a half wavelength, and therefore that is 1/4. And this is the exact scenario that we have over here. Okay, we have a node met with an antinode. I promise I'll get to answering the question soon. If we look at our third harmonic, we can see successive nodes right here. So this is a half right here. However, we see another pair of node met with another antinode, and so this is a quarter. And so therefore our length is equal to 1/2 plus 1/4 of a wavelength, and therefore our length is equal to 3/4 lambda. Now let's finally move on to our fifth harmonic. We get two successive nodes right here, and then another pair of successive nodes right here. So this whole distance is a 1 wavelength, and again at the end we have a node met with an antinode, and so this is 1/4. And so our length is equal to 1 plus 1/4 wavelengths, and therefore our length is equal to 5/4 lambda. Okay, so just by going through these examples, you can see that we cannot produce even harmonics. And the reason why we can't produce even harmonics is, like I said way back when I was starting to answer this question, it's because of the fact that we must have a node on this end and an antinode on this end. And what that always results in is this 1/4 of a wavelength at the end of each harmonic, okay? Because even in this case and in this case, when we have an even number of 1/4 wavelengths, right? Because this section right here is 1/2, which is equal to 2/4. So we have an even number of 1/4 wavelengths. Again, because of this 1/4 at the end, it becomes odd. Every time we plus an odd number to an even number, we get an odd number back. And same thing over here, we have 1, and that's equal to 4/4. So we have 4 lots of 1/4 wavelengths plus that 1/4. So we're plussing an odd number to an even number, and so we get an odd number of 1/4 wavelengths, okay? And so you can write that theory as an answer. When the train was approaching at a speed of 5 meters per second, he heard a frequency of 139 hertz from the clarinet. Showed that the frequency of sound heard by the clarinet player would have been 137 hertz. Alright, so this is obviously a Doppler equation, therefore we can use our Doppler equation, where our perceived frequency is equal to the source frequency times the velocity of the wave, all over the velocity of the wave minus the velocity of the source. Again, using minus in this case because we are approaching our observer, okay? Now we want to find the source frequency because we're trying to find the sound heard by the clarinet player. So we can rearrange for our source frequency and we get our perceived frequency times the velocity of the wave minus the velocity of the source is equal to the source frequency times the velocity of the wave. Therefore, our source frequency is equal to the perceived frequency times the velocity of the wave minus the velocity of the source all over the velocity of the wave. Now plugging in our numbers, we get 139 times the velocity of the wave, which is given up here as the speed of sound of 341 meters per second, 341, minus the source velocity, which is given up here as 5 meters per second, all over 341, and this gives a source frequency of 136.96 Hz, and therefore we can round this to 137 Hz. A second clarinet player was standing beside Belliot as the train approached. She produced the same frequency, 137 Hz, as the clarinet player on the train, causing Belliot to hear beats. Explain why the sound wave reaching Belliot from the clarinet on the train did not have a frequency of 137 Hz, and explain why Belliot heard beats, and calculate the beat frequency. Alright, so the reason why Belliot did not hear 137 Hz is because our clarinet player on the train, which we can model as a dot, okay, as the train moves, this causes the clarinet player to catch up to previously emitted wavefronts that is produced by the clarinet, okay? And so as the wavefronts move forward, the clarinet player is also moving forward. And so what this results in is the wavefronts in front of the clarinet player to be munched up, but the wavefronts behind the clarinet player to be spread out. Now, we know that the clarinet player is approaching our physicist, okay? So our observer is right over here. And therefore, Belliot, which is our observer, is going to perceive shorter wavelengths compared to the true wavelength. And therefore, as the velocity of the wave, right, the speed of sound, is constant, therefore as v is equal to f lambda, therefore our perceived frequency is equal to the velocity of the wave all over our perceived wavelength. And as our perceived wavelength is shorter compared to the true wavelength, our perceived frequency would be higher compared to the true frequency, okay? And we could see that in the previous question, because in this question it says that he heard a frequency of 139 Hz, even though the clarinet player was producing a frequency of 137 Hz. And we can calculate our beat frequency, where we know our beat frequency is equal to the absolute value of f1 minus f2. We can say that f1 was the frequency that Belliot was hearing, which was 139 Hz, and f2 was the true frequency, which is 137 Hz. Okay, therefore plugging in our numbers, we get the absolute value of 139 minus 137, and therefore this gives a beat frequency of 2 Hz. Alright, so now why does he hear beats in the first place? Beats are caused by two waves that have very, very similar frequencies. However, because their frequencies are not exactly the same, if we were to observe those two frequencies from a fixed position, the two frequencies are going to come in and out of phase. When the sound waves meet in phase, they constructively interfere, therefore producing a loud sound. However, when they meet out of phase, they destructively interfere, therefore producing a quiet sound. And as I said before, because they continuously come in and out of phase, what that's going to result in is us hearing a loud, quiet, loud, quiet, loud, quiet, loud, quiet sound. And that gives the sensation of beating. That's why it's called beats. And so you can write that in yourself. Mike and Kate are on a tramping trip and they're crossing a suspension bridge. They realize that by jumping up and down in a particular way, they can set up a standing wave in the bridge. The bridge is 24 meters long. Describe one difference between a standing wave and a traveling wave. Alright, so there are multiple answers to this, but one of the answers that you can say is that standing waves do not transfer energy, however traveling waves do. Alright? Or we can also say that standing waves have fixed points of nodes and antinodes, or we can also say that a standing wave requires two sources to interfere with each other, however a traveling wave does not require this. And then coming off that last point, standing waves require interference because we need two sources to interfere with each other in order to produce those nodes and antinodes. However, again, traveling waves do not have this requirement. And so you can write any one of those in. A bridge can oscillate at many harmonics. Show that the frequency of the third harmonic is that equation right there, where L is the length of the bridge. Alright, so we can model a bridge as a string that is fixed at both ends, and therefore we'll have a node at this end and a node at this end, okay? And therefore we'll have an antinode over here, and therefore our first harmonic will look like this, okay? Where our length is equal to half a wavelength. However, we're interested in the third harmonic, okay? Again, we would have a node over here and a node over here, antinode in the middle, antinode over here, node over here, node over here, antinode over here, and therefore this produces our third harmonic like so. And as you can see, our length is equal to 3/2 of a wavelength, okay? Our first half, second half, third half, okay? So this is the equation that we're interested in. From here, we can say that our wavelength is equal to 2L all over 3, and that's equal to our wavelength. We also know that V is equal to F lambda, and so therefore we can plug this equation into here, and we get V is equal to F times 2L all over 3, like so. And so now dividing both sides by this expression right here, we get V divided by 2L all over 3 is equal to our frequency, and therefore we can rearrange this as our velocity times 3 all over 2L is equal to our frequency, and therefore 3V all over 2L is equal to our frequency, and as you can see, that is the exact same equation that we're trying to find. The bridge oscillates at the fundamental frequency with a period of 1.8 seconds. Calculate the speed of the waves in the bridge. Alright, so we know that V is equal to F lambda. We know that our frequency is equal to 1 over the period, okay? And we have a period of 1.8 seconds, so we can simply plug that in. And this gives a frequency of 5 over 9 hertz. Okay, I'm gonna keep it as a fraction in order to keep whole values. All right, as for our wavelength, we again can model this bridge as a string that is fixed at both ends. All right, and we are interested in the first harmonic, and so our length is equal to 1/2 of the wavelength, and so therefore 2 times our length is equal to the wavelength. It says all the way up here that our bridge is 24 meters long, and so therefore 2 times 24 is equal to our wavelength, and this gives a wavelength of 48 meters. And so now we can simply plug in our numbers and we get the velocity is equal to 5 over 9 times 48, and this gives a velocity of 26.67 meters per second. There we go. Mike is 6 meters from one end and Kate is 6 meters from the other end. Give a comprehensive explanation of how it's possible for Mike and Kate to cause the bridge to oscillate in the second harmonic. In your explanation, you should draw a labeled diagram of the bridge oscillating in the second harmonic, explain how they set up a standing wave, and explain why they chose to stand in the position stated, and explain the phase relationship between their oscillations. Alright, so let's first draw the second harmonic. Again, we can model this as a string that is fixed at both ends, and so we have a node over here, a node over here, a node in the middle, and 2 antinodes in between. And so therefore it looks like this, like so. Now we know from the beginning of this question that this whole length is 24 meters, okay? And therefore we can split this wave into 4 sections, like so, right? 1, 2, 3, 4, okay? And we know 24 divided by 4 is equal to 6. And so therefore Mike is standing over here and Kate is standing over here. Okay, so this will be 6 meters, this will be 6 meters, this will be 6 meters, and therefore this will be 6 meters. And obviously 6 times 4 is equal to 24. And so as you can see, Mike is standing 6 meters from the edge, and so is Katie, okay? So now, as Mike and Katie jump up and down on this bridge, they're going to send transverse waves along the bridge, and then when those transverse waves hit the closed end, they will reflect and be inverted 180 degrees. And therefore, those 2 waves that are produced by Mike and Katie are going to interfere and produce a standing wave. And the reason why Mike and Katie must stand 6 meters from the edge is because this is where the antinodes lie, okay? And so therefore, when Mike and Katie jump up and down, this causes the bridge to have a max amplitude at that point, okay? You can imagine that if they were to jump in the middle, for example, they would instead produce the first harmonic as it would look like this, right? If they were jumping up and down in the middle. Now, if you have seen a standing wave either in a simulation or in a video in real life, you would know that it would actually look something like this instead, okay, right? The 2 parts of our antinodes are going to be 180 degrees out of phase and it will kind of oscillate like this. And so therefore, Kate and Mike must jump 180 degrees out of phase with each other, okay? And so therefore, Mike and Kate must jump at a period of 0.9 seconds. And the reason for that is because that is half of our total period for the entire wave. Alright, and you can write that in words. Priya wants to measure the wavelength of her green laser. She shines her laser beam through a diffraction grating. She sees an interference pattern on the wall behind a diffraction grating as shown in the photograph. The slits in the diffraction grating are 2 times 10 to the negative 6 meters apart. The angle between the central antinodal line and the first antinodal line is 15.4 degrees. Show that the wavelength of her green laser is 5.31 times 10 to the negative 7 meters. Alright, so we'll use our trusty equation, and lambda is equal to d sine theta. We are measuring from the central antinodal line to the first antinodal line, and so our n value is equal to 1. And so therefore we can simplify this equation and say that lambda is equal to d sine theta. We are given our d value right here, and we are also given our angle, and so we can simply plug in our numbers. Times 10 to the negative 6 times sine 15.4 degrees. And this gives a wavelength of 5.31 times 10 to the negative 7 meters. There we go. Explain what causes the bright spot at the first antinode. So as a green light passes through our diffraction grating, okay, this green light is going to diffract at multiple regions through this diffraction grating, right? There are thousands of slits, and therefore as each slit acts as a point source, there are going to be thousands and thousands of sources of light. And therefore these diffracted waves are going to overlap and interfere with each other. And therefore when the path difference between the waves is 1 is obviously a whole number, and therefore this is going to result in constructive interference as the waves are meeting in phase and thus producing a bright spot, which we can call an antinode. And so you can write that in. The picture at the top of page 7 shows the pattern she sees using the green laser. Priya repeats the experiment using a red laser, and red light has a lower frequency than green light. Draw the pattern she would expect with the red laser and explain why this pattern is different to the green laser. Alright, so before I draw it in, let's go through the theory so we know what's actually going on. We know our n lambda is equal to d sine theta, okay? And as red light has a lower frequency than green light, okay? Red light has a lower frequency, and therefore as the speed of light is not different between red light and green light, they're both light, so both waves will travel at the same speed. Therefore, red light will have a greater wavelength when compared to green light. As red light has a greater wavelength than green light, as both lasers go through the exact same diffraction grating, our d value remains constant, and therefore the only thing that can change is our theta value also increasing. Okay? And so what that means is that our maxima will be further apart. So we would still have our central maxima in the exact same spot, okay? That doesn't change. However, our first order maxima and our second order maxima will be further apart, like so. Let's draw it over here and then over here, okay? And if you want, you can draw the central one much bigger because it's going to be brighter. And then these ones can be slightly bigger, and then these outer ones will be the smallest because those will be the dimmest, okay? Priya shines white light through another diffraction grating. There are 3 complete spectra of visible light produced on each side of the central antinodal line. Calculate the minimum slit separation of this diffraction grating and explain your reasoning. The frequency of violet light is 7.7 times 10 to the 14 Hz, and the frequency of red light is 4.3 times 10 to the 14 Hz. So just like in the previous question, let's go through the background theory before we answer the question. If we have our diffraction grating right here, and we are shining white light through it, okay, and we have our wall on this side. For our central antinodal line, okay, our central maxima, this is our n is equal to 0. We know that for this line, this is where our path difference is 0, and therefore all light meets at that point. And so if we shine white light through that point, obviously our central maxima is going to be white. However, for our higher orders, our n is equal to 1, and n is equal to 2, and n is equal to 3, right? And obviously they'll be the same on the other side as well. We can see from the question that 3 complete spectra of visible light are produced, okay? And what that just means is that we will see like a rainbow. Okay? The reason for that is because white light consists of all visible wavelengths of light. And because white light consists of different wavelengths, obviously the different wavelengths have different wavelengths. And so because n lambda is equal to d sine theta, because all the wavelengths are going through the same diffraction grating, our d value remains constant. However, let's take red and violet, because these are our 2 extremes of our rainbow spectrum, okay? Visible light spectrum. We can see that red has the lowest wavelength and violet has the highest frequency, and therefore as red has the lowest frequency, it must have the longest wavelength, and as violet has the highest frequency, it must have the shortest wavelength. And so therefore, using this equation, we can see that for red light, as our n lambda is equal to d sine theta, because our wavelength is the largest, we are going to diffract the most, right? So our angle is going to be the greatest. However, for our violet, our n lambda is also equal to d sine theta, right? The equation does not change. However, because we have the shortest wavelength, our angle is going to be the smallest, and so therefore we're going to diffract the least. And so for all our higher orders, we're going to have complete spectras, and violet, this is blue, I know, it's not violet, but violet is going to diffract the least, and red is going to diffract the most within our maxima, okay? And if you want more on this, you can watch my second video on interference, and it's towards the end where I look at this in more detail, okay? Now, how does this relate to calculating the minimum slit separation for this diffraction grating? Because we know that n lambda is equal to d sine theta, okay, we can see here that we produce 3 complete spectra on either side. And so therefore our n value must equal to 3, okay? And we also want to set theta to 90 degrees, okay? Because we want to calculate the minimum slit separation, what this is going to mean is we're trying to make d as small as possible, and therefore we want our theta to be as large as possible. And the largest our theta can be is 90 degrees to our central maxima. Okay, obviously light isn't going to come through here and go backwards. That's not how it works. So 90 degrees is the largest angle. All right. And as for our wavelength, the wavelength that we'll be using is the wavelength of red light. The reason for this is, like I said over here, this is the reason why I went through the theory. As we can see, red light diffracts the most. So when we get to our third maxima, our third order maxima, the red is going to diffract the most. And so our red is going to be on the outer edge. And so in order to calculate the minimum slit separation, we want to calculate it with the light that's going to be at the edge, which is going to be red light. And so now we are ready to rearrange for our D, and we get D is equal to n lambda all over sine theta. Now sine 90 degrees is equal to 1, and so therefore D over n lambda all over 1 is equal to D is equal to n lambda, okay? Now we established that our n is equal to 3, however we do not know what our wavelength is, but what we do know is that v is equal to f lambda, and we know that we're dealing with light, and we know that the speed of light is equal to 3.00 times 10 to the 8 meters per second, okay? And we are given the frequency of red light right here, and so we can simply plug in our numbers, and we get lambda is equal to v all over f, and therefore 3.00 times 10 to the 8 all over 4.3 times 10 to the 14, and this gives a wavelength of 6.97 times 10 to the negative 7 meters. Now plugging this into here and this into here, we get D is equal to 3 times 6.97 times 10 to the negative 7, and this gives a D value of 2.09 times 10 to the negative 6 meters. There we go. And with that, we're done. See ya.